Today we start the transportation problems, and we will start with the modeling part, and we will talk about how it happens, what's going on there. But what's the transportation problem? Now, transportation problem is a model where you have to move some goods from supply points to demand points. You have some supply points. They can be your factories, your storage points, or something entirely different. But still, you have some sort of supply points, and you are trying to move goods from those supply points to your demand points. Now, this is most of the time it's a minimization problem for cost, but other stuff can creep up sometimes. Other, optimization objectives can be there, but most of the time it's a minimization problem, and we treat it as a minimization problem when we are trying to solve the problem. So if there's a maximization version of it, you can just switch it to minimization by multiplying everything with a negative sign. So you can just treat every transportation problem as a minimization problem if it's easier for you. So we have some set of supply points. So it's M supply points, and now we can have N demand points and some variable cost. Now these three will define our model, but this is a special model. It's still a linear problem, yes, but it's a special problem, and we can treat it as a special problem, and we don't need to use normal simplex to solve it. We can do something that's easier, okay? Easier than normal simplex, at least, and iteration-wise, let's say, number of calculation-wise, or it's something new, so it's something a bit more different, but still. Now, if we have M supply points and N demand points, those supply points have these are a constraint set. So I have M constraints from my supply points, and it says that, okay, if my supply is S1, my total supply, okay, the amount of units I am signing from that S1, that first storage, for example, U1 units, should be less than or equal to S1. And if I have a demand point, which has a demand of D1, then those units sent, let's say U1 again, should be greater than or equal to D1, so that we make sure that we meet the demand. There will be some cases where we don't need to meet the demand, but this is not it. In transportation, we are trying to meet the demand. If we cannot meet the demand, we will deal with it in a special way. You will see. It's the same for supply points as well. We can have more than enough supply or less than enough supply, depending on how what kind of a problem we are facing. We're going to deal with it accordingly. But still, we have a variable cost in here as well, and this variable cost is the cost of transportation for 1 unit of good. So we actually have M plus N constraints, but there will be something a bit different from our normal simplex in here. We will have M point N constraints, and remember, when we are talking about constraints, we said that, okay, number of constraints is equal to number of basic variables, but it's not like this here. In here, we will have M plus N minus 1 basic variables. You will see what I'm talking about soon enough. So this is the basic model where we can see this is the, as I said before, unit transportation cost times the number of units we are sending from point I to point J, and Xij, this is the variable, and this Xij should be greater than Dj, which is the demand at point J, and this Xij should be less than or equal to Si, which is the supply of point I. So this is our basic transportation problem model. It's a closed form. But when we are talking about transportation problems, we're not going to use the closed form. We're going to use a special table for that one. Now, this is the table. As you can see, on the left side, we will have supply points, and on the top side, we will have demand points. Now, each supply and demand point has a cell for it. So, for example, supply point 1 and demand point 1 has this cell, and this cell has this variable x11, which means that the number of units sent from supply point 1 to demand point 1, and it will have the cost over here, C11. So this is basically the modeling of the transportation problem as a transportation table. Instead of using this model, the closed form, we're going to use this table because there's a simple iteration we can make. It's called the transportation simplex, to solve the transportation problem through this table instead of using the simplex tables, the bulkier and heavier and harder to follow simplex tables. Because think about it, there are M supply points and demand points and M times N variables. At least M times N variables, which are X variables. You will have also E and S variables as well, slack and access variables in here as well. So it's a lot of variables, which we don't want to deal with. Instead of that, we are gonna deal with the variables in here, only the variables in here. We will add a supply or demand, which you will soon see soon enough, but we may not always have to add them. It's a dummy demand or dummy supply. We will get there soon enough, but still, we will just deal with these variables, m times n amount of variables, and making them in a table, it's easier to follow. Table like this. Instead, if you want to use normal simplex, they would all be in a row. All the variables will be in a row, and it will be extremely hard to follow and solve. This is much easier. So what we need to do is just balance the transportation problem first. As I said in the previous slides, you can have more than enough supply or not enough supply. So if you have more supply than your demand, excessive supply, then you will have to create a dummy demand, which will mean that, okay, this is the supply that you're not sending anyway. That dummy demand is the supply you're not sending anyway. You can create, you can produce that supply, but you're not sending it anyway. Or you will not produce it, you will not manufacture that item, maybe. It's up to you. But that dummy demand will help you decide which of your supply points is going to be sitting idle, not doing that production or not sending those units. Same for the other way. If you have less than enough supply, then you will need to create a dummy supply, a supply point that is not going to be producing anything, literally, and not going to be sending stuff, but it's going to show us who we are not sending those stuff to. For example, let's say that we have 2 customers and each of them have a demand of 10, and I can only produce 15 units from one supply point. So I can either send those 15 units by sending 10 to one customer and 5 to another, or sending 7 to one, 8 to one, or sending, I don't know, 5 to one, 10 to the other one, etc. But still, I need to have 20 units sent. I can only send 15. So I will just create a supply that has a dummy supply that is a limit of 5. So I will just say that, okay, the first supply, which is the real supply point, will send 10 to the first customer and 5 to the second customer. And the second supply, the dummy supply, the one that does not exist, will send 5 to the second customer, which means that the second customer will not be getting those 5 units, okay? They will have a shortage. That shortage is shown through the dummy supply point, okay? The dummies, either supply or the demand, are showing our shortages and excessive amounts, okay? But still, we have to balance those. So we are going to use those dummy versions of it, okay? You'll see what I'm talking about soon enough, the excess supply and the unmet demand stuff. So for example, PowerCo has 3 electric power plants that supply the needs of our cities, okay? Each power plant can supply the following number of kilowatt hours of electricity. For the first plant, 35 million, second one, 50 million, third plant, 40 million. Okay, the peak power demands in these cities, which occur at the same time, which is 2 p.m., are as follows in kilowatt hours again. City 1 is 45 million, City 2 is 20 million, City 3 is 30 million, and City 4 is 30 million. The cost of sending 1 million kilowatt hour of electricity from plant to city depends on the distance the electricity must travel. Formulate an LP to minimize the cost of meeting each city's peak power demand. Now, the table is missing over here. There should be a distance table, but still, this is the model. These are the distances, as you can see, 8, 6, 10, 9, 9, 12, 30, etc. This one was missing, but I will add them and change them later on. But still, these are the costs for sending those, and these are the supply constraints and the demand constraints. Now, this is the normal linear model, but we want to model this as a transportation table, which can be shown like this. As you can see, we have 3 supply points, power plant 1, 2, and 3, and they have supplies of 35, 50, and 40. And 4 demand points, City 1, 2, 3, 4, and they have demands of 45, 20, 30, and 30. Now, first we have to check if the total supply and total demand are equal. We are checking 35 plus 50 plus 40 is 125, okay. 45 plus 20 plus 30 plus 30 is 125 again. So yes, they are equal. No problems there, we will say. then we have to start solving this, but we're not getting there yet. This is just a table, okay? We'll just make sure that this table is balanced. Both the supply and the power and the demand have the total of the same total number, okay? 125. But if it was different, for example, if we said that demand for city 1 is 40 million kilowatt hours, now this has decreased from 125, now we have 120. We are, we have excessive supply, more supply than we need. Okay, we have 125 supply, but we have only 120 demand. Then now we need to create another demand point to be able to balance this table. So we're just gonna create a fifth city, a dummy city, something that's not really there, something that's not gonna have any cost, okay? But it will be part of the solution because it's gonna show us which power plant is not working fully. We have to pick which one is not going to work fully, because we cannot say that, okay, we have a demand of 120, but we will just produce 125 anyways. That 5 million kilowatt hours is going to be wasted. We're just gonna electrify the ground. We just ground it and keep going. No, you cannot do that. You have to make sure that you just produce 120 at that point so that you can minimize your cost, not the transportation cost, but your production, your generation cost. So over here, we're gonna make sure that we have another city, another demand, because the demand is lacking. Demand is less than the supply at the moment. So we'll just add another demand, which has a demand of 5, demand point, which has a demand of 5. So this dummy will have values of 0, cost of 0. Why? Because we're not really gonna send anything there. We're just putting it there for show. It's not really there. It's just showing us which power plant is not going to work. And now we say, okay, we will solve this. We will make a solution. We don't really need to find a solution right now, but one of those points, for example, this one, is going to end up being 5. And we will just say that, okay, power plant 2 is not going to supply 50, but it's going to supply 45. This 5 in the dummy column means that it's not going to work at full strength, okay? It's not going to produce everything. It's not going to generate the electricity, all of it. It's just gonna waste those 5, okay? It's not waste, but not gonna produce that 5, okay? Instead of 50, it's gonna produce 45 to be able to meet the demand fully and not give excessive electricity, excessive amounts of electricity. So this is what happens when we have more supply than we need. What about the other way around? What if we had less supply than we needed? What if the demand was greater than the supply? For example, if the demand for city 1 is 50 million instead of 45, the original 45, if it's 50 million, then now we have a demand of 130. This is more demand than we can, meet. Okay, this can't be met because we only have a supply of 125. So this time we're gonna add a dummy supply. Okay, a dummy power plant, something that's not there. Okay, this is the shortage version of it. This is the shortage of demand. So from supply. So when we add that shortage dummy, now we know that one of these power plants, all of these power plants will work at maximum capacity, but one of these cities, 4 cities, is not gonna have its demand met. And check the question, it's changed as well. We are told that the penalty of unmet demand is $80 for each million kilowatt hours. So if you don't meet a demand, we pay $80 for each kilowatt of hour. Now we know that we're not going to meet 5 million kilowatt hours, so we're going to pay 5 times 80 for sure. But this 80 could have been different for each city. For example, it's 80 for every city, so the cost is 80, 80, 80, and 80 over here. But it could have been different. It could have been 80 for city 1, 120 for city 2, 75 for city 3, and I don't know, 2000 for city 4, for example. So if they were different, we would just write the costs accordingly in the different way. But this dummy shortage supply of 5 is just used to balance the scales for supply and for demand. And this, as you can see, has a penalty. If it didn't have any penalty, it would have values of 0 with it. It doesn't really matter. Just like the dummy demand point. But if it's shortage, if it's a dummy supply point, then it can have penalties like this one. So this is the basic way of balancing stuff. Okay, let's keep going then. There is another problem over here. 2 reservoirs are available to supply the water needs of 3 cities. Okay, 2 reservoirs, 3 cities. Each reservoir can supply up to 50 million gallons of water per day. Okay, each city would like to receive 40 million gallons per day. Okay, now 2 reservoirs with 50 million capacity. Okay, which means 100 million total. 3 cities with 40 million demand, 120 million. The demand is greater than the supply. Okay, we will have a shortage version. Let's keep going. For each million gallons per day of unmet demand, there's a penalty. Okay, there's a shortage, hence there's a penalty. At city 1, the penalty is $20. At city 2, the penalty is 22, and at city 3, the penalty is 23. The cost of transporting 1 million gallons of water from each reservoir to each city is shown in the table. So these are the transportation costs. So we're just gonna find the table. Just model this as a table. Okay, the costs are simple: 7, 8, 10, 9, 7, 8. Okay, we're just gonna write these just like this, and then we're gonna add the penalties in the bottom: 20, 22, and 23 with the dummy, the shortage supply. So what we have here, the cost, the transportation costs. Oops. The transportation costs and wait. Okay, sorry for that one. The penalty costs and transportation costs, and now we have at the bottom the demands of each city, 40, 40, 40, and the supply of each reservoir, 50 and 50, and the shortage amount, 20, which is 120 total. So we're gonna solve this one later on. But when we solve this, we're just gonna find the right, values, the assignment of each reservoir to each city, and how much, how many gallons of water they are sending to it. For example, we'll just say it, okay, reservoir 1 should send 50 or 40, because the total demand is 40 million gallons of water to city 1 and 10 million gallons of water to city 2, for example. We're just gonna solve this one. And after the solution is, done, we will see the numbers. And this is the optimal solution over here. As you can see, we're gonna send 20 million gallons of water to the first city and 32 second city. So the total supply is 50. 20 plus 30 is 50. For reservoir 2, we're gonna send 10 and 40 to 2 and 3 respectively, for a total of 50. And the shortage is going to be from city 1. City 1 is not gonna get 20 million gallons of water, so just the half of it. From 40, they're gonna get 20. Instead of 2 and 3, we are penalizing city 1 because it's giving us the least amount of penalty possible, I guess. But still, this is just the optimal solution. It might have been different if the costs were different, but it's what it is right now. So as you can see, each row and each column has the same total. 20 plus 30 is 50, 20 plus 20 is 40, 30 plus 10 is 40, 40 equals 40, and 20 total, 10 plus 40 is 50, 20 plus 30 is 50. So each row and each column has the same total. This is always like this. We are trying to find a balanced version. So the first model we talked about, the first, let's go back. Yeah, over here. These values, these greater than or less than values, actually become equalities. We are trying to switch those values into equalities by adding another constraint, another, dummy supply point or, demand point. Now, when we add this, let's go to the last part once again. When we add this dummy shortage, we are getting another constraint over here, one more constraint over here, but we are also getting 3 more, for this question at least, 3 more variables. This one, and this one. So we add more variables and another constraint. When we add a dummy, either a supply or a demand, we get more variables and one more constraint. So this is okay. We can model other problems as transportation problems as well. For example, we can just model a balanced transportation problem, an inventory problem as a balanced transportation problem. This is something you will just remember when you see, I hope, the Sailco example. Remember this one? It was the first complex model we had talked about. It could be modeled in 2 different ways. And now this is the third way. We can just, actually the third way looks like the second way we have talked about before, but still, this is just the inventory model being, modeled as an inventory problem, modeled as a transportation problem. Now we have different points. Now these are supply points. These are our inventories and supplies. So we have the initial inventory point. This initial inventory is a supply point because it's just giving something to the system, okay? It's just presenting us with extra units to use. And now we have the overtime and regular time productions. So we have a total of 9 supply points, and we have a total of 5 demand points. So there's a quarter for the first, quarter 1 demand. There's a quarter 2, quarter 3, and quarter 4 demand, and we are trying to, balance the problem. So it's a dummy demand point. This dummy demand point is the supplies we don't use, we don't generate, we don't produce, or we don't manufacture. So we don't want to use everything over here. These are our maximum capabilities. Okay, we can produce this much. These are the maximum values, but we don't want to use everything. So we're just gonna assign them to a dummy demand point so that we know that they will not be used. When we try to model this one as a table, we get this. Now, this looks a bit more complex, but still, this is the same, same rules, same modeling things apply. For example, we have 9 supply points, so it's going to be 9 rows. We have 5 demand points, so it's going to be 5 columns. So 9 rows, 5 columns. The initial and the quarterly, supply amounts are given over here, as you can see, 4150, 4150, 4150, and 10 for the inventory. So they're written here, as you can see, and the demands are written down here. Now, what about these costs in there? We already know the costs. Let's go back and see. So we have, let me see, where is it? Yeah, 20 cost of 20 per sailboat for holding, carrying, inventory costs, etc. So if we carry something, if we hold inventory, it's going to cost us $20. Okay, and there is the produce up to 4 sailboat at a cost of 400 per sailboat. If you work overtime, it's 450 per sailboat. So 400 for in the regular time, 450 in the overtime for the first period. But if we produce in the first period and send it to the second one, we add 20, the inventory cost. Instead of 400, we get 420. Instead of 450, we get 470. If we, again, use regular time and in the first quarter and send it to the third quarter, we hold this 2 times, so double the inventory cost, 400 plus 40. And for the fourth period, triple the inventory cost, 400 times 460. Now this is for quarter 1. What about quarter 2? Well, from quarter 2, I cannot send back to quarter 1 because this question doesn't allow that. But it might have been possible if it allowed it for backlog and sending back. We are sending back, but we're not making time travel. We're just saying that okay, this is late delivery. If it allowed late delivery and there was a penalty for it, it would have been written here instead of the big M. Big M says that it's not possible, it's not allowed. This is such a huge value. It's like 10 billion, for example, or something greater when compared to here. It's big enough. It could even be 2000 because 2000 is big enough when compared to 400, but still make it very big, very large. So the M here means that you cannot do this. You cannot produce in the second quarter and send it to the first. Or you cannot produce in the first third quarter or send it to the first 2, or you cannot produce in the fourth quarter and send it to the first 3. These are not allowed, so they have costs of M. And as you can see, after we have modeled this, and this is the dummy, zeros, all zeros, 570, we can see that, okay, the initial inventory is just sent or used for the first quarter. And in the first quarter, we are producing in regular time 40 boats, 30 of which is used in the first quarter, 10 of which is held in the inventory and sent to the second quarter. There is no, overtime in the first period, so 150 is sent to the dummy. The dummy means that this is not used, this is not done. So we're not using 150 units of overtime over here. The second quarter is much simpler for, regular time, just produce 40 and use it in second. Okay, but in overtime, we are producing 10 and using it second, and we are not producing 140. This is the capacity, unused capacity for us. Okay, 140 unused capacity. Out of 150 available, we're just producing 10, and we're not using the 140 points of overtime capacity. In the third quarter, we are producing 40 for the third quarter in regular time, and 35 overtime for the third quarter, and we are not using 115. For the fourth quarter, we are producing 25 in regular time. We're not producing anything in overtime, and this 50 of excess production we're not using. Okay, so 25 is used for the fourth quarter and 15 capacity is unused. The dummy means unused capacity once again. So we can just, this is the optimal solution, by the way, but finding the optimal solution is another story. So this is just a modeling part. Okay, this is how we model stuff. What about finding the feasible solution now, optimal solution? Now, before we find the optimal table, we need to start with a basic feasible solution. In, for example, in normal LPs, in normal, linear program models, we always started with S and E values. Remember that one? We had S values and E values, and our starting table, initial table, had no X values in it. It's either E, S, or artificial values, of course. Artificial variables had values, but never the X values. In here, as you can see, we don't have any S or E values. They are all X values. They are all decision variables. We don't have any slack or excess values because they are all equalities right now. And we don't need any artificial variables in here. All of these variables here are X values. So we need a basic feasible solution that's different than our, regular linear program models, let's say. We need something that has only X values, that is basic variables with X. Now, check this one, the number of basic variables we have. As you can see, any value written in a cell means that it's a basic variable, and any cell with no value in it is a non-basic variable. Let's check the number of basic variables. 1, 2, 3, 4. Dummies are basic variables as well. 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 basic variables. Okay. How many constraints do I have? 3, 6, 9 over here, 10, 14. So 14 constraints, 13 basic variables. Yeah, that seems right. Normally, as I said before, we were looking for 14 basic variables for 14 constraints, but in transportation problems, they are all equalities. So we don't need the 14th one because they are linearly dependent on each other anyways, because we know that the sum over here is 10, the sum over here is 40. These are all summations, so all these basic variables are linearly dependent on each other. We don't need the last one. So we are always looking for n plus n minus 1 basic variables in a transportation table. This is important, don't forget that part. So 14 constraints and 13 decision variables, basic variables, sorry. We have actually more than, let's see, we had 3, 6, 9 over here, 45 decision variables. Out of these 45 decision variables, only 13 of them are basic variables. The rest, 32, I guess, yeah, are non-basic variables. So how do we find this basic feasible solution? Because we need a basic feasible solution to do that. Now, we have 3 different ways of doing that, the basic feasible solution, but still we're gonna check how we can make mistakes first, then we will start making the correct version of it. But the thing is, as I said before, we have n plus n constraints, we need n plus n minus 1 basic variables, but those basic variables must form a loop or must not form a loop, let's say. You will understand what I'm talking about soon enough, because when you take those basic variables, if you take these basic variables like this, okay, we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 constraints, right? So I will need 6 basic variables. If I pick these basic variables like this, let these 6 be the basic variables, I cannot find a feasible solution because these 30 and 30 for 63 and 64 will not be, met. Those two demands will not be met because these are all non-basic variables. So there are no values summing up to 30 over here or here. So this is an infeasible solution. I cannot just pick any 6 cells and say, okay, let these be the basic variables. No, there should be a method. There should be some, logic to finding those values. So I should make sure that I can find a loop by adding one more point to it. You will understand what I'm talking about. First, we need to see what a loop is. Okay, loop is an ordered sequence of at least 4 different cells. Okay, if any of 2 consecutive cells lie in either the same row or same column, for example, like this one, as you can see, we can have more basic variables around, but a loop is always like this. Okay, I'm trying to find a loop, so I'm trying to find something like this or like this. All those corner points are a basic variable. Okay, all these corner points are a basic variable. This is the loop. In a normal situation, let's go back. You shouldn't be able to find a loop over here unless you are making iteration. Okay, loop comes with an iteration actually. So this need to not form a loop when it's not an iteration. When it's iteration, it needs to form a loop. So, for example, this cannot be a basic, not basic, yeah, basic feasible solution, because these form a loop without iteration. We'll get to iteration soon enough, but still, this is a loop as well, as you can see here. These are just going linearly, but this is not a loop. No, neither is this a loop. This cannot be a loop as well, because when you are going from one corner to the other, you can pass over non-basic variables, or you can pass over basic variables, but still you cannot be using them as part of the loop. Okay, if this was just like this 4 points, then it would be a loop. But this is 4 points, but it is going sideways, diagonally, so this is not a loop as well. But this is a loop, 4 points. As I said before, you can have basic variables in other places as well, but this one is forming the loop. You just pick one loop out of them. So to be able to find, you will understand what I'm talking about when we start finding the solution. But the loop is very important in the iteration, you will see. Now, when we're finding the basic feasible solution, we will want to start with one of the three methods: the northwest corner method, the minimum cost method, or Vogel's method. And these are in order of increasing complexity. Northwest corner is the easiest one to apply, but it gives a simple, very simple initial solution, and it may make you, force you to make lots and lots of iterations till you find the optimal solution. Minimum cost usually gives a good starting point, and you usually make much less iterations to find the optimal solution. And Vogel's method can actually give you the optimal solution sometimes. You may not even make any more iterations after you use Vogel's method, but still all of them can be used, and you can just come up with new methods of finding the basic feasible solution. But it's up to you. These three are the most common ones. So what about the northwest corner? Well, northwest corner says that start at the northwest corner, the top left corner, and make the assignment you can make the most, and then keep going by deleting rows and columns accordingly. Now, what does this mean? For example, we don't need to know any of the costs over here. Let's say that this is our demand and supply table. You can see the supplies over here, 513, and the demands over here, 2421. Now, first check if they are equal. If the sum of supplies and the sum of demands are equal. If this is a balanced table, 513, 9, 2421, 9 again. So this is balanced. And start at the top left, the northwest corner. So the northwest corner, this cell can have a value of 2 at most, because this demand is 2, so the total cannot be greater than 2 in this column. Okay, sum of the variables in this column cannot be greater than 2, so this can only have a value of 2. If we give this value of if we give this cell a value of 2, as you can see here, this column is eliminated. We are not looking for this column anymore. We are not looking at this column anymore, so we only have this 3 by 3 matrix left. Now we skip to the next northwest corner, which is this one, the top left now, the new top left corner, because we are looking at this one anyway. So this is the new top left corner. So from here, I can see that this is either 4 or a 3. 3 is smaller, so this can only be 3. So I will add a value of 3 over here. And this one, this row, is eliminated because we have met this demand now. Sorry, we have met this supply now. There is no demand in there anywhere. So it's gone. We don't need to check it anymore. And from there, we will just keep going and going, okay? We will just try to find new points. So this is as this row is eliminated, this is this now is the new topmost corner, the left top corner, northwest corner. Now, there's a small problem here. Both the row and the column is 1. So if I add 1 here, I'm gonna need to eliminate both of them. But if I eliminate both of them, I will have a problem, because I'm gonna need to find a total. For example, we have 3 supply points and 4 demand points, so 7 constraints, which means 6 basic variables, right? But if I eliminate both of them and just add 1 here and eliminate both of them and eliminate both this row and this, eliminate both this row and this column, I will have only 2 more spots left, right? And I will just say, okay, this is 2, this is 1, 1, 2, 3, 4, and 5 decision variables. basic variables, but these 5 basic variables are not enough. I need 6. So when that happens, when you see the supply and demand is equal to each other at the point you are eliminating, at the point you are filling up, you have to make sure that you eliminate only one of them and keep the other as 0, so that you can add another basic variable that is a value of 0 over here. So just add a basic variable of 0 over here and then eliminate the other one. Okay. When you are filling a cell, when you are adding a value to, assigning a value to a basic variable, you cannot delete 2 constants at the same time. You have to delete one of them only and add a 0 to the other one at any place. I could have eliminated this one and add a 0 over here or here as well. That would work as well. Same solution, no problems there. It's just arbitrary. We have eliminated this one, this column, and added a 0 over here, as you can see. As I said, you could have added a 0 here or here as well. One of them though, just one of them, because you need a total of 6 basic variables. Now we have 2 spots left, and this is going to be a value of 2, and eliminate this column. And this will have a value of 1. And yeah, we'll be done here. When we add 1 over here, we're done. So this is the most basic method of finding a feasible solution. So the northwest column works like that. What about the minimum cost? Well, with minimum cost, now you need to see the costs. The supply and demand values are not enough. Now you need to see the cost as well, because with minimum cost, you just go and find the least cost possible in the table and add the most possible value to it. So in here, 1 is the least cost over here. The minimum cost is 1. So I'm gonna find the most units I can add over here, which is 8, because 8 and 10 has a minimum value of 8. So I will add 8 over here. When I add 8 over here, this column is eliminated. It's gone. And this drops to 2 from 10. Okay. Now what else? We have 2 over here, 2 over here. So I have to pick one of those 2 and add a value in there. Now, in this question, in this form, in this table, it doesn't really matter which one I pick first, because the other one will be added anyways, because I will have to, add values to them anyways. But if I pick the, let's say this one first, I will add a value of 2 over here, and this column, this row, sorry, will be eliminated, and this will drop down to 10, as you can see here. And then again, I will pick this 2 because it's the least value anyway, the minimum cost again. So I will add a value of 5 over here, which will eliminate this row and make this, demand drop to 5, as you can see here. Now, 2 rows are eliminated, 1 column is eliminated, and we have 3 points left. And I will just add 5, 4, and 6 over here. As you can see, 5, 4, and 6 will be added over here, and we are done with the minimum cost method. So we can just find, a better solution, because with Northwest, you would be just adding adding values over here, and then here maybe, and going like this, and there would be no logic to it. Okay. I mean, there's a logic to it, but no real optimization logic to it. But with minimum cost, you're just trying to pick the minimum values in there, okay, so that you can find a better solution at the start. Vogel's method, on the other hand, is the most complex among these 3, but it gives the best starting point possible most of the time. Not always. It might even give you an optimal solution if you're lucky, but it's not guaranteed. Sometimes the minimum cost might be better from it or equal to it. That happens, but most of the times Vogel is better. Vogel's method is better. So it says that you just pick the 2 smallest costs in each row and column and find the penalty value for not, assigning to the least value in there, which means that let's take a look at this table. 6, 7, 8, 15, 80, 78. Now, for the first row, the least possible costs, 2 least possible costs are 6 and 7. So the difference is 1. If I don't give the, cost of 6 its most possible, supply or demand, 7 can take over for it, for this, row. So instead of 6, I can use 7. It's not that much of a penalty. What about the second one? 15 and 78. Wow, there's a penalty of 63. If I don't give 15 what it needs, I have to be, dealing with 78 instead of 15. Wow, that's too much. Huge penalty, 63. What about the columns instead of the rows? 6 and 15, just a penalty of 9, I'm okay. 7 and 80, wow, penalty of 73, and 8 and 78, penalty of 70. So these are huge penalties, as you can see here. So I have to pick the greatest penalty and get rid of it first, which is 73. So I have to give whatever I can give to this point so that I don't need to deal with 80 later on, which is a value of 5. Now, if I give this one a value of 5, this column is eliminated. And this will drop down to, this supply will drop down to 5. So now I don't need this, as it's eliminated, I don't need to, calculate anything anymore. And these penalties on the other columns will just carry over, because this column will not, change the penalties for these two columns, but it might change the penalties for the rows. So it's gonna be, we have to calculate the rows once again. 6 and 8 has a penalty of 2, 15 and 78 has a penalty of 63. So still the most penalties over here with 70, which means that I'm gonna have to give this the most value I can give, which is going to be 5. But if I give this point a value of 5, both the supply and the demand, both the row and the column are being eliminated. So I have to use another, dummy variable, let's say, and give it a value of 0. I can either give a value of 0 over here for this row or over here for this column. I have to pick one of them. It doesn't really matter which one I pick. I'm probably going to give it to this one. Yes, supply is 0 over here, and this one is limited. So it's going to get a value of 0 here. And this one is going to get a value of 15 over here. And we're done. Because of the starting point, Vogel has probably given us the best answer, but we have to check how that happens. To be able to check how that happens, we will have to get into transportation simplex, but transportation simplex is a bit more complex. So first you have to understand how these starting solutions work, how they are found, and then next lesson, which is in 2 weeks, I guess, because next week we have the midterm, we will start with the transportation simplex and keep going on from there.